Welcome to This Explainer. Today, we're diving into something literally mind-bending. We're going to talk about a brilliant, real-life cheat code that physicists invented to understand the universe. If you've ever felt completely bogged down by the sheer complexity of classical physics problems, tracking every single angle, direction, and invisible force, well, this approach is a massive breath of fresh air.
Really think about it for a second. What if physicists actually found a way to bypass all the messy, headache-inducing math that we normally associate with tracking how objects move? What if, instead of drawing a million different arrows pointing in every conceivable direction, there was just a completely different paradigm altogether? Well, there is, and it absolutely changes everything about how we view the physical world.
Okay, let's dive into Section 1, Newton's force headache.
To really appreciate the cure, we kind of need to understand the headache first. So let's look at the classic, force-based way we are usually taught physics. The absolute bedrock of classical mechanics is Newton's second law, right? Force equals mass times acceleration. It's beautiful, it's elegant, and it works wonderfully for simple, everyday trajectories like throwing a baseball. But here's the catch. Force and acceleration are vectors. That means they always have a magnitude and a direction. To solve a complex system using Newton's laws, you literally have to track these complex 3D directional arrows for every single particle at every single millisecond. And as you can probably guess, in complex systems, that becomes an absolute nightmare.
Just to give you an idea of how quickly Newton's laws can get out of hand, imagine a torus, basically a donut shape, rolling across a horizontal table. Now imagine there's a tiny pearl sliding around perfectly inside that rolling torus. To figure out where that pearl is at any given moment, using Newton's laws, you have to calculate these constantly changing constraint forces. These are the invisible physical forces that the walls of the torus exert on the pearl just to keep it trapped inside, all while the torus itself is spinning and moving. You'd basically be drowning in 3D vectors trying to track all those shifting angles. It's a complete mathematical headache.
Which brings us to Section 2, the energy alternative. So, how do we escape this vector nightmare? Well, we pivot to Joseph Louis Lagrange and his 1788 masterpiece, Mécanique analytique. He completely reframed the entire problem. The contrast here is stark. Newtonian mechanics is basically this chaotic web of 3D arrows, obsessing over forces and getting bogged down trying to find every single physical constraint. Lagrangian mechanics, on the other hand, treats energy like a simple bucket of water. It completely ignores those messy constraint forces keeping our pearl inside the torus. And the best part? Energy is a scalar. It has no direction. We're essentially trading a chaotic, tangled web of vectors for simple, directionless quantities of energy.
So, the crucial point here is the core definition itself. The central equation of this entirely new paradigm is the Lagrangian L equals T minus V. It's just the total kinetic energy of the system minus the total potential energy. That is literally it. This one single function summarizes the dynamics of an entire complex system without needing a single vector arrow in sight.
Just to ground this abstract math in physical reality for a second, let's break down what those two letters actually represent. T is kinetic energy, right? The energy of motion. Basically, how fast are the parts of the system moving? And V is potential energy, the energy of interaction or position, like the force of gravity pulling down on our system. By simply looking at the difference between the energy of motion and the energy of position, Lagrange managed to unlock the secrets of the entire system.
Moving right along to Section 3, Path of Least Action.
But you're probably wondering, how does knowing just the energy actually allow us to predict movement? Like, how do we know where the pearl goes without ever bothering to measure a physical force? Well, it all comes back to Hamilton's principle. This principle tells us that out of all the possible, chaotic, crazy paths a system could take from point A to point B, the universe is remarkably efficient. The actual path taken by any system will always perfectly minimize a quantity called action, which mathematically is just the Lagrangian added up over time. It's almost as if the universe naturally calculates the path of least resistance or the path of least action.
So here is the elegant procedure, the literal cheat code in practice. First, you pick any generalized coordinates that make sense for your specific problem. It could be an angle, a distance, whatever is easiest for you. Second, you calculate the kinetic and potential energy. Third, you write out the Lagrangian, L equals T minus V. And finally, you just apply the Euler-Lagrange equations to find the motion. Notice what's missing? You don't have to draw a single force diagram. Physicists essentially invented this brilliant calculus hack just to completely avoid doing the hard, tedious math of tracking Newton's constraint forces.
And this brilliantly illustrates why the hack actually works so well. It's deeply rooted in D'Alembert's principle.
Think back to the wall of our torus pushing on that pearl. That force is always exactly perpendicular to the direction the pearl is actively sliding. And in physics, a force that acts perpendicular to motion does zero work. Because these constraint forces do zero virtual work, mathematically, they just drop completely out of our energy equations. They're just there to keep things on track, which means we can entirely ignore them when doing the math.
And that sets us up for Section 4, the universal physics hack.
Now, you might think this is all just a neat mathematical trick for solving textbook puzzles with beads on wires or rolling toruses, but it is so much bigger than that. This energy-based formulation literally scales to the entire cosmos. Think about the history here. We started with Newton's basic laws in 1687. Then, in 1743, D'Alembert realized we could basically ignore those pesky constraint forces. Lagrange perfectly packaged that idea into his beautiful energy equations in 1788. But skip ahead to 1948. The legendary Richard Feynman took this exact same Lagrangian concept and applied it to quantum mechanics, creating quantum path integrals to track subatomic particles. This cheat code evolved over centuries to become the foundational language of modern physics.
Oh, and the Lagrangian gives us another massive, absolutely crucial gift, Noether's theorem. The brilliant mathematician Emmy Noether proved that if you look at your Lagrange equation and a specific coordinate is just missing, say the equation doesn't depend at all on where you are in the x-axis, that symmetry instantly reveals a conserved physical quantity, like momentum. Just by looking at the structure of the Lagrangian's energy equations, you instantly know what fundamental properties of the universe are being perfectly conserved. It's like magic, but it's just pure, elegant math.
Let's zoom out a bit and look at how this builds into the very fabric of reality. Look, Newton's laws are fantastic for everyday life, but they fundamentally fail when things get too fast, too heavy, or too small. But the Lagrangian? It survived. Whether we're talking about the deeply curved 4D spacetime of general relativity, or the bizarre wave function interference of quantum mechanics, when Newton's vector arrows completely break down, Lagrange's scalar energy equations just keep working perfectly. We rely on them for electromagnetism, classical field theory, you name it.
So as we wrap up, I want to leave you with this incredibly mind-bending thought, one that's directly derived from Feynman's quantum discoveries. If the Lagrangian shows us that particles will always take the path of least action, how does a particle actually know which path that is before it takes it? Does the universe somehow calculate every single possible path instantly in the background, or is the very nature of reality simply perfectly falling into the path of least action? It's a profound question that shows how a simple math hack, originally designed just to avoid drawing force vectors, ended up unlocking the absolute deepest mysteries of our universe. Thanks for joining me on this explainer. Keep wondering and keep exploring.